not much more than that. And I figured I'm online already. I am online. Okay, very good.
So we're just teaching to the camera today.
Correct, correct. But that's okay. That's okay. I'm gonna put this in a this kind of presentation mode.
And
Or
this
should I
is
put this
Not
the
this one.
last
should, this
last
one?
lecture was always about recap.
It's a recap
Just
here
you
too.
need to go there actually.
Because what I have here is this one. Large deformations, summary how to prepare yourself the midterm exam.
This year we don't have any railway thing.
No, Xinkin is not here. We were expecting her to come to see us, but eventually she decided not to come. The railway is a lot of, it's a,
It was fun.
it's a fun because it's so unique.
Correct.
No, nothing else compared to railroad dynamics because it's like so weird.
So Aki, just like distribute the questions to these students, and also
Oh
we
yeah,
will make the code available once if you have the questions.
yeah, yeah. So
Until Friday, it will be
correct,
released.
correct. Okay, so I see that only one viewers, and that's you. So no one else is even following
I
that.
think
So
you need to start first.
yeah, yeah, we'll do that. We'll do that. So is it gonna be? Let me just see the how is. By the way, this the screen is really good now. A little bit this side. Let me see which one is that side. Can you turn that a
No,
little
no,
bit?
no, no, don't run that. Wait.
Okay, so you do it like that.
Should I now?
Yeah, this is really good. Okay,
Most of the
thanks guys.
Okay.
yeah, yeah, that's it.
Very good. Okay, thanks guys. So I'm gonna collect my stuff and everything. So it's gonna be just 30 minutes, 45 minutes max.
Okay. Nice one.
By the way, another day I was watching these YouTube recordings to see what were the things that I explained, and I realized sometimes the mic is some kind of breaking a little bit.
I think it's because of the network, not because
Is
of
it
anything
because
else.
uh,
It's not because of
it
anything
was
else.
understandable, and I put this close capturing on. It was okay. It was able to understand me, but it was a little bit unpleasant because of the this kind of a breaks in my voice.
Hmm. It's just the network, nothing else.
Just the
Someone
network.
is here, I think.
What the heck, guys? You're not allowed to come here. Well, yeah, now you made my life difficult because now you need to put this on the screen too. Okay, so let's see how it goes.
Just,
That one,
yeah, that's it.
but we need to put the lights
Yeah,
back.
yeah, I put it on the.
Okay, can you please do that?
Yes, yes, yes.
Yeah, sorry about that
Yeah, no worries.
because you're the only ones here. So if you can watch this online, that would be great.
Okay, that's it.
Fantastic, fantastic.
So I'll be here in half an hour.
Yeah, and I promise that it's going to be 45 minutes max,
Okay.
and then we off. So there's at least one decision we need to do later today, and that's related to when you guys would like to have next midterm exam.
Should I turn this off?
Yeah, yeah. Let's put it down. Oh, maybe wait, maybe is there a way to put this bigger here? No.
No, because you need to connect this with the projector.
Yeah, yeah. Let's just put it off.
Right now we can see this one. I think there might be.
Yeah. Okay. Here you go. So this is for you then.
Thank you.
But now I don't see any questions, comments. But that's okay. That's okay.
I'll
Thanks,
ensure
guys.
that there will be
And there's today is a big day. Today is a big day. Big. You know why?
one.
And I can give you a hint. It's not because of the Labor Day party is coming soon, but it's bigger than that. Much bigger than that. Sura's got his driving license. Fantastic. So so the degree goes like this: bachelor, master, doctor, driving license. So he's a little bit beyond the doctor degree, and he made it. He made it.
Congratulations.
Okay, see
Hey,
you. Okay,
yeah, see you. See you. Okay, guys. So what I will do, by the way, why is that you guys are not participating in these Labor Day parties? Because this morning when I came to my office, I noticed that they are deassembled this party place. It was in this parking slot next to the university. Yeah. Okay. All right. Anyways, so last lecture. So I'm not planning to come next week. So like I promised, so we're gonna close the case about large deformation. We'll not spend too much time on that. And then summary, a list of questions that you can expect to see in midterm exam. And big discussion, of course, is when is it we're gonna have the midterm exam. And I have a proposal, and I would like to announce that already. And my proposal is from 2nd of May, not 1st of May, because that's kind of like a holiday. It's like a Christmas kind of, not for me, but for students. I couldn't care less about that day. But for you, it's a big deal. So I guess that is against the law to get started the exam on 1st of May. So the 2nd of May it will get started and it will be closed on 8th of May. How that sounds? Would that be okay? All right. Okay, now can you guys take a look if there is somebody from online complaining against? Or should I lock myself? Yeah, I don't find it easily. So if you can see if there's anyone complaining against that proposal. They don't complain. Okay, very good, very good. But let me get back to you regarding the material and regarding the dates exactly. But prior to that, a little bit about the large deformation cases, and then how to prepare yourself the midterm exam. Well, large deformation, or this is something that I explained already 3 weeks back. So there was a material a little bit about what is the deal with these absolute non-coordinate formulation. We're gonna go and take a look at about the element technology. And if you're familiar with the finite element method, I don't know if you guys ever participate the course entitled finite element method or something like FEM, sometimes called that. You did not. All right. Anyway, so I'm gonna speak a little bit about different types of the elements and then applications. And I think that the most fun part is this application part. Okay. So, but 3 weeks back we discussed about this big picture, why it makes sense to describe large deformation. This is of course related to very complex examples like a belt, bully cases, or clothes, or drapes, or airbags, or something that you can actually see very large deformation. It's not at all the models that you need to take large deformation into account. This large deformation is heavily used and it's kind of needed, particularly in a biomechanical application. Not so much in the machines. These belt and bullies are special system and there is dedicated software to analyze them. But if you somehow would like to make a model that there is a belt and bully and mechanisms, then it actually makes sense that you are more or less familiar with this technology. Okay, but again, the big dream within multi-body community is that everything started from rigid bodies, and then they were extended to flexible bodies by assuming that the deformation is small. And now people would like to get rid of this assumption and they would like to model large deformation. And that's possible with the absolute non-coordinate formulation. And the special deal about the formulation is this. So it makes it possible to model reference motion and deformation using very simple kinematics. And the simple kinematics is a matrix of shape function, which is what you already are aware of, and the vector of nodal degrees of freedom. That in conventional finite element method is limited to small deformation and limited to describe something that is not rotating much. Here, we're going to make a special trick to enhance that equation such that it can describe both very large reference motion, translation and rotation, and large deformation. And how we can make that happen was based on this vectorization procedure. And the vectorization procedure was the one that is shown here. This too was explained a couple of weeks back. So if in a conventional beam element, we have a degrees of freedom that are displacement in a transverse direction, and that differentiated with respect to length of the element. Now what we're going to do is that instead of using scalars, we're using vectors. And these vector quantities makes it possible to increase the number of degrees of freedom per nodal location. And because of this feature, it allows you to describe this large translation and large rotation and deformation. But now, important thing is that, you know, if you take a look at the how much we have a nodal degrees of freedom in one end of the beam element is already 4 degrees of freedom. 4 degrees of freedom. And it becomes to be confusing, like 4 degrees of freedom. So what it means, it's going to be more confusing when we're going to take a transverse Z deformation into account. But 4 deformation already is something that is not easy to understand. And what it means here is that, of course, there is a position, the translation in X and Y direction, that's going to be 2 degrees of freedom, and rotation, that's your third. The fourth is related to axial deformation in that particular location. Already a little bit confusing, and it becomes to be more confusing when we're increasing the degrees of freedom in one nodal location. All right. So this is an element that is based on center line description. So we're parameterizing the element using the center line only. Center line is something that is very often used, but assumption related to this center line parameterization is that now we need to make an assumption that the cross section is always perpendicular with respect to the center line. And that's not necessarily the case. There are cases where this is not a very accurate representation. This happens when you're dealing with the transverse Z deformation. And transverse Z deformation, I don't know if you're aware of this thing, happens when you have a short and relatively thick structure. This is where you can see that transverse Z deformation is started to make a significant contribution. It's kind of like, I don't know if you have ever made this kind of case that you have a number of layers that you're building your beam structure by using number of layers, and then you press it in the middle. Then you see that these layers are moving with respect to each other. And this is because of the transverse shear that takes place. Now, if you're not allowed this transverse shear to take place, you're screwing these different layers together. This force that is trying to separate them is more like trying to separate these layers. That's just transverse Z deformation. And because of the transverse Z deformation, cross section is not perpendicular with respect to the midline. Now that's a big deal, because then this whole idea of line parameterization is not working anymore. Conventional finite element method, they do this such that they have a separate interpolation for midline. And okay, let me take a look. Is this is my okay, so it disappeared. Very blurred picture, by the way. I don't know if it is better in your computer.
Yes.
Much better.
Yeah.
Okay, all right. Let me see if I have my pen with me. Here it is. It seems that they're out of the battery, so no, it's it's a presentation mode that is not allowing me to do that. Okay, anyways, shortly, what they do in a conventional finite element method is that they have one set of interpolation for midline, another set of interpolation for cross-section orientation. And those two things are separate, and they are coupled in the definition of elastic forces. So that's what they do, And that's what makes it possible to describe transverse Z deformation. Now, this method that assuming that transverse deformation to be insignificant is called Bernoulli beam theory. And now if you take the transverse Z deformation into account, that is called Timoshenko beam theory. Now, Timoshenko beam theory, we can take transverse deformation into account, but in the absolute Noda-Konner formulation, this is going to be a little bit cumbersome. It's going to be a little bit cumbersome because then we need to include slopes in a transverse direction. So if we originally have the slopes in axial direction, now it needs to be supplemented by slopes in transverse direction. Number of degrees of freedom per nodal location, and we're still in a two-dimensional case, increased by 2. So it was 4, now it's 6. And now it becomes to be even more complicated. And it will be more complicated when we're going to extend this to three-dimensional space or plate elements. So this is the plate element and how the plate element look like. Now, each of the nodal degrees of freedom, we have a total of 16 degrees of freedom, 16. And in the case of plate, excuse me, this is in the case of plate. In the case of beam, it's going to be the same number of degrees of freedom. And it's important to understand what they are standing for, because if we have a 16 degrees of freedom per nodal location, 6 of them are easy to understand. So there are translation, 3 direction, rotation, 3 direction, but the rest is not so easy to understand. And what these rest are standing for are cross-section deformation, how the cross-section itself will deform. And it can have several different deformation modes. The 6 of these deformation modes are describing how the cross-section itself deforms. All right, but now if you do this, then you can use a very general continuum mechanics approach to describe your elastic forces, and you can capture very complicated cases with the heavy penalty of computational burden. So it's going to be computationally very expensive to carry out. Okay, anyway, so this is how it looked like. Now this is related to how the elastic forces can be accounted. And like I say, it looks very bad. It looks very involving, but actually it's not that bad because, you know, this large number of degrees of freedom makes it possible to treat the element like a continuous, like solid elements. And then you can use this continuum mechanics approach, and then you can use a different material models and so on and so forth. So that's the way to go. Yes.
How does the absolute nodal coordinate handle contact and friction between the flexible bodies?
Oh, that's a good question. So what about if there is two beams that are colliding, they are contacting to each other? Okay, this is going to be the ways you can model that is recommended to model that by using this penalty formulation. That there are forces, like forces that are separating the two beam elements from each other. This is how it is recommended to do it. There are studies that is being modeled also by using this non-smooth dynamics, but that's not the recommendation here. It comes with a complicated math with practically no benefit. So penalty forces, you just separated your elements by penalty forces. Very good. I don't know what to say because I thought that you guys are thinking, okay, all right, so it's gonna be another 30 minutes and then I'm back to the party, and but you were obviously listening to me. What's wrong with you guys? Okay, all right. So then, this is the case that you remember this Jussi Sopanen and how he was able to discover that there's something wrong in the element. And something that was wrong in the element was called locking, which is I was asking from these guys, what's wrong with you? Because it's a Labor Day time, you guys should be having a parties and everything. You're here. All right, so this Jussis opponent was the guy that recognized that there is something that is called locking. This locking, by the way, is very common in finite element method. It happens very often because of it's an approximate method, so it's not exact science, so it's an approximate method. And it's very common that particularly when you're dealing with these shared deformable elements, Timoshenko-based theory, then there's a locking. And the kind of weird story in the locking is that it becomes because inconsistent kinematics description, shortly speaking. So you're making a mistake in your kinematics. And very often it is fixed by making additional mistake in the numerical integration. When you are defining the elastic forces, when you're defining how is that you can compute the elastic forces, it typically based on the numerical integration scheme. And this numerical integration scheme is based on Gaussian integration points. I usually use enough points to make an accurate solution. But some people recognize that if you're using less than it is needed, this problem you made in your kinematics will be somehow compensated. So the story is this: you first make a mistake in your kinematics, then you make another mistake to compensate your first mistake. And the result is very good. So it works fine. So it's quite surprising. All right, but this is what shows the locking. And the locking is that, like you can see in the figure that is below here, convergence is almost non-existent. So when you have this case B here, the solution is not correct. It's getting better and better and better, but you need hundreds of thousands of elements to make this to be acceptable. This is what is called locking. So it's ultra low convergence. It converges eventually, but no one can afford to have that many elements that it actually converts to correct solution. So that is called locking. And here too, there's many different ways how you can solve the lockings. One of the ways is that you can start playing with the number of degrees of freedom in your node allocation. You can deal with the high order and very low order elements. And I don't know if you ever met the Dr. Marko Matikainen. He's one of the teachers. He used to be academic fellow in the Department of Mechanical Engineering. So he is specialized to this high order, a little bit about the low order elements, but particularly high order elements. So he making all kind of tricks to make increase in the degrees of freedom per node allocation. Comes with the computational cost, but comes with a certain benefits as well. So he's very good in that, and introducing a lot of different varieties in that regard. Okay, now many of these cases, many of the studies made by using the absolute node formulation are academic cases. They are like academic verification. Is this method capable to correctly compute this and that? And one of the good verification cases is called flying spaghetti. That is a very flexible structure that is flying in space, and it's flying because there's a force and a moment imposed to it. And then you just see how accurate is your computing, how fast is your computing. And of course, this is like in scientific or engineering scientific, let's say engineering scientific Olympic competition or competition of some kind. So there's a competition, here's a rule, who can compute these the fastest, and then the game's on. And then the people can recommend their approaches, and then people are monitoring how fast is this method and how accurate it is. This is very common. This is one of the verification cases, and it's like this. So it's, I don't know how, is it here? Yeah. So it comes after a little while. But there is this very flexible body that is flying like this. Very extensive to compute. Very difficult to compute. And then you're just comparing your results against that is already published. Here are the cases that is being used in the belt and bullies. This is a belt drives. First two-dimensional case. So this is a beam element based. This is a plate element based. And now it's being extended to Xerox machine to see how the paper goes in a Xerox machine. And this too is a plate element based, like this. And then there is special elements for cable dynamics. Okay, then the special element is something that is called, this ALA comes from the word arbitrary Lagrangian Eulerian formulation. Arbitrary Lagrangian Eulerian formulation is a special formulation that you can change the length of the element while you compute it. So this is very beneficial in a cases like a belt and pulley system, because what is difficult in the belt and pulley? So let me see if I can, yeah, here's my pointer, is this part here that is in contact to pulley. This is hard to compute. Whereas this part that is from the pulley to the payload is very simple to compute. You don't need that many elements to compute this straight line here and the dynamics related to this particular part of the belt structure. But you need a lot of to do it here. If you do not use this arbitrary Lagrangian Eulerian approach, the length of the element is defined by the diameter of the pulley. And there's no way that you can make it any different than that, because it's possible that cable that is located here will be in touch with the belt, with the pulley. And now if it is in touch in a pulley, you have to use a certain minimum length. That you cannot make it longer than that. Now the idea of the arbitrary Lagrangian Eulerian formulation is that you can change the length. And this is where the theory is based on. Very beneficial in the cases like this. I don't see much of a use in other cases. All right, then there is cases where it is being used to catenary system. This is a catenary system that is used in the trains. It's being used in tire analysis. It's being used in a leaf spring. Leaf spring, by the way, is a quite an amazing component because it's still being used. You still see that in a heavy vehicles. You can still see that in other applications too. It's amazingly complicated to analyze because it experiences large deformation. That's how it works. And there are contact between the beams as well. This is what you asked earlier. So now there's different layers. They're in contact with each other, and it's not easy to compute it. And they're also pre-strain in the structure. Sometimes very stiff, very significant pre-strain. So, but you can use this formulation in those applications as well. Biomechanics comes here. Then there's very exotic cases like nano-electrical mechanical systems, fluid pipe conveying system. So there's a fluid inside of the pipe, and how the system is behaving in like cases like this. Optimization of the manipulators, that's possible too. And now comes this interesting thing, because it's been showing that the method is very close to something that is rational, non-uniform rational B-splines. And this is the technology that is used in CAD software. So if you're making drawings, geometries in CAD software, they are most commonly based on NURBS, because in NURBS you can make any geometry you want. Polynomials are a little bit limited. Polynomials you cannot make like a perfect shape of the circular like a ring. That's gonna be hard to do it in absolutely correctly. Whereas NURBS, you can make it happen. Now, in finite element method, the most of the time spent is for meshing. So it goes in such the way that you have a design of the car, like a front bumper of the car, like case like this one here. Then you're taking the geometry from your CAD software. You put the mesh top of the geometry, but it's not easy. And it's not easy because there are sometimes very minor details which making these meshing tools to be confused. And the example could be that there is a very small drilling somewhere here. And now because of that, this meshing tool started to put a lot of elements to this particular detail that may not be very important for us. Then you need to go back to the CAD software. You need to take this drilling away, mesh it again, and you need to go back and forth. So now there is an idea that what if not going back and forth, but based on your finite element technology, entire technology for NURBS. You know, remember what we did in the very beginning of our discussion about finite element method. We said that our finite element technology is based on polynomials. But I said that if you guys are not happy with the polynomials, you can use something else too, like trigonometric functions or maybe even non-uniform rational B-splines. Now there's an attempt that everything is replaced by NURBS. Instead of using polynomials, there's a NURBS. And this is something that is called isogeometric analysis, because it's going to be very good to describe the geometries correctly. There's no problem there. And it helps to contact description as well, because now the contact is, the geometry is exactly how it appears in reality, not based on these small linear pieces, but it's smooth like you see in a reality. So this is what is called isogeometric analysis. I don't know how well it is already adapted in a commercial finite element software, but interesting extension from a conventional finite element method. All right, I have this conclusion here. So everything is based on this vectorization procedure. That's what the absolute corner formulation is based on. And it can be used in vehicle dynamics, biomechanics, rotating structures, optimization, multi-physical analysis, cable dynamics. And then I have one in-class quiz here. What is an isogeometric analysis? Would you guys like to answer this, or you don't want to play with me today? You want to play? Or not today? Yeah, okay. Very good. So just a second. I'm gonna video capture display. I'm gonna put this off and display to you. Okay, so let me see. Yep, it's on. Okay, and I'm gonna start sharing my screen again. Windows capture. No, this is not looking very good. So it's okay, yeah, I want to use a display capture. This one. All right. So the options are. Yes, it is, because I skipped all that. The others were something we discussed earlier, because this was the only one left. Okay, so in isogeometric analysis, so this is not the same that in you say that this is not the same that in a PowerPoint. Yeah, you're right about that. Yeah, this is supposed to be like this. Yeah, it's somehow confused. So what do you guys think? What is the correct answer? Correct. So it's a one. Finite element based on NURBS. That's what the isogeometric analysis is about. Finite element based on polynomials is what? Conventional finite element method. Finite element based on trigonometric functions is non-existing. Imaginary functions, non-existing. So that's what it is. Very good. Midterm exam. Like I said, my proposal is this. Oh, let me take this in the way that this can be edited. My proposal is this. One attempt, 1 week time. What do you guys say? Is it okay or not good for you? One attempt. Yep. Is it okay? So it's okay. All right. Very good. Correct. And then again, you have this voting action, so you can vote one question that will be taken away, and one question that will be there for 100% certainty. Okay, and the topics are listed here. So the topics are, there are 6 different topics: artificial intelligence, past multi-body system dynamics, biomechanics, contact modeling, stress analysis in multi-body dynamics, multi-body systems in fatigue, and large deformations. So large deformations and multi-body systems in fatigue and stress analysis rated as a 2-star, whereas the contact and the visiting lectures are rated as a 4-star. Okay? And questions are here. So the questions that we could ask, sorry that this is a little bit of small font, but artificial intelligence plus multi-body system dynamics. Okay, let me change this view to be okay. These ones. Each of these are explained in the recording that we made a week ago. So what is artificial intelligence? Name at least 4 subfields. What is the role of virtual models and simulation in developing assistant and autonomous systems? Which recent developments make machinery automation feasible? They are all addressed, so they are not easy, but again, remember, if there is something you feel that is overly difficult, you can vote it out. Here are the questions that are related to biomechanics, a total of 5 questions. And 2 of them are highlighted, meaning that they are more important than others. And again, this is something that you can get the answers when you look at the recording from the biomechanics. Okay? Then the contact modeling, the possible questions are this one here. Explain the concept of bounding boxes. That's the concept that is based on contact detection. Remember, the contact consists of 2 steps: detection and the contact modeling itself. Okay, bounding boxes was putting these boxes, big and small ones, around the object and looking whether or not these big boxes can collide. And this is the way you can detect possible contact. Not modeling, but detect it. All right. How the contact can be modeled using penalty forces. So it's based on this penetration, how much the objects are penetrating, and this is the way you can push them aside, away from each other. What are the advantages and disadvantages associated to penalty force approach? Simple, but it's sensitive for time integration settings because too much penetration will introduce too heavy forces and system becomes to be unstable. Is not able to handle very big mass differences, again because of the penetration. So if you have a very big mass, say 5 tons, very small mass, 1 gram, you cannot model that properly because of the mass difference is so huge. And what is a many-body dynamics? Many-body dynamics is same than non-smooth dynamics, where the contacts are based on these inequalities. You said your model that they can do whatever they want, except they cannot penetrate. And this is modeled by using these inequalities. This is what can be used in many body dynamics, having a lot of bodies. All right, then here are the things. So this is a contact description. This is the bounding box and different layers in a bounding box. This is 2 different ways that the contact can be described. Penalty forces, use of cone complementary approach. That's it. Stress analysis, only 1 question. And that's how the stress history can be evaluated using multi-body system dynamics. So that's simple. You build your system you want to analyze. You run it that in several different work cycles. And then you're recording strains that you can get by modeling your structure to be flexible or taking your forces to external finite element model. And that's the way you can estimate these strains and stresses. If you are modeling your structures to flexible bodies, then you can use something that is based on modal stress matrix. You can get all the stresses, all the strains automatically from your flexible structure. Problem is that sometimes this is not available because of the software incapabilities there to communicate. So this is something that you need to be careful. The first typically is available, but it's a lot of computing that is not necessarily needed. Multi-body dynamics in fatigue. Why welded structure are vulnerable for fatigue damage? Why is that they can easily get fatigue damage? And the reason was that because the welding process itself, uh, oh, this is not, okay, because of the welding process itself, you can introduce this initial crack. And because of the welding process itself, you're going to have very high residual stresses due to the heat loading introduced. This is a very bad combination because even the small loading will introduce a local, very local plastic deformation, and that's how the crack started to grow to your structure. All right, this was the way that the fatigue can be analyzed. Large deformation. When this transverse shear plays an important role, that's when you have very thick structures. That's when it plays an important role. Concept of isothermic analysis is based on NURBS. So the NURBS are used as the fundamentals of the element technology. It helps meshing. The meshing will be more straightforward. And explain short the kinematics used in the absolute nodal coordinate formulation. Kinematic used is something that there is only this shape function matrix multiplied by vector of nodal coordinates. That itself is capable to do all this you need, meaning large translation, large rotation, large deformation. Okay, so Shur has promised to put the voting on right after the lecture. That is going to be in, later today. So please vote. The voting will be closed sometime this week. Then we will let you know which question will be in the exam paper and which question will not be there. Rest may or may not. Not many questions. So I would say that this is doable. Very much doable. What do you guys think? Not bad. Not bad. I like that. Very good. Okay. So as promised, 45 minutes max. So 1 minute left. So I'm gonna take this off. And it's gonna be